Hello, welcome to the lecture on 4.2. Today we're going to talk about the natural exponential function, the number e. This is just called the natural exponential. There's no reason that we should come to this number naturally using exponentials. There's a reason for it, but it's beyond the scope of this class. It doesn't really matter. So what I want to talk about first is what e is. What is the number e? It's actually an irrational number. It's 2.718288182845904523, and it keeps going forever. Non-repeating, irrational number. So how do we actually get this number? Well, there's actually a pretty easy way to go about it. It's not intuitive. But if we let y be this, and we look at what happens to y as n goes to infinity. So here, the exponent is going to infinity, but also the base is going to infinity. So as the exponent increases, first of all, this number is bigger than 1, so this value will increase in value, but also this number is decreasing. So our base is decreasing as our exponent is increasing to infinity. Right, but as n goes to infinity, y actually approaches the number e, this number here. The natural exponential function. The natural exponential function is the exponential function f of x is equal to e to the x, as you probably guessed, with base e. It is often referred to as the exponential function, as if there's only one, but there's obviously more than one. There's a whole family of exponential functions. We just often refer to it as the exponential function when we, in certain contexts, when it is obvious what function we're talking about. Let's give you a graph of what this looks like. And yes, it's going to look identical to the functions that we talked about last section. We still cross at 1. We still have a horizontal asymptote of y equals 0. And we still go to infinity as x goes to infinity, just like everything else. Now, because e is equal to 2.7182a ... we have that this function is actually between 3 to the x and 2 to the x. 2 to the x would actually be above over here and below over here. And 3 to the x would be below over here. It would cross here at 0, 1, and then it would be above. And that should make sense based on where this is between 2 and 3. Now, if you haven't noticed already, the domain of this function is all real numbers. And the range is 0 to infinity, just like the other ones. This base holds some special properties, one of which you'll see in calculus, one of which you'll see in the next subsection, the one we're about to talk about. The next section I want to talk about is continuously compounded interest. Recall, from last section, we talked about compounded interest, and we had a formula for it. A of t is equal to the amount after t years, but the formula is p times 1 plus r divided by n to the n times t power, where p is the initial principal, the amount that we invested initially, r is your annual interest rate, n is the number of times that we compound our interest per year, t is the number of years for which we leave the principal alone to collect interest. Also, recall that for the formula, y equals 1 plus 1 over n to the nth power. This will approach e as n goes to infinity. So as our n gets very, very large, infinite, this sequence will approach e. Okay, now I want you to look at this formula here versus this formula here. Now, they're very similar, very, very similar. But you have to remember what n represents in our formula a of t, in our function. Remember, n represents the number of times per year that interest is compounded. So if interest was compounded monthly, then n would be 12. If interest is compounded every 6 months, n would be 2. So we have a few numbers for n and what they mean. Now, what I want you to think about is what if we wanted to compound our interest daily? That would be n is equal to 365. But what if we wanted to compound our interest more? What if we wanted to compound our interest continuously, as the subsection title gives away? What if we wanted to compound this interest not even every second of the year, but more than that? Just continually add our interest into our principal. Well, then what we would get is this. As n is going to infinity, this would be going to e. So what I'm going to do here is do a few manipulations in order to get the next formula that we're going to use for continuously compounded interest, right? So I'm going to rewrite this as p times 1 plus 1 divided by n divided by r. So if you remember, when we are dividing fractions, a over b divided by c over d is equal to a times d divided by b times c. Specifically, that we flip the denominator and we multiply. So this, written in this way, is identical to this term here. R over n is the same thing as 1 divided by n divided by r, where n over r is in the denominator. And I'm going to have my nt here. So I have an identical statement. I just rewrote it. It's a different form. Now, what I need to do is match this. Notice that this n matches this n. They're the same term. They're the same exact variable. Here, our variable is a little bit different. We have an n over r here, and we only have an n here. So I need to rewrite this a little bit. So what I'm going to do is divide and multiply by r in the exponent. So we have 1 plus 1 over n over r to the n divided by r times t, like this. So notice all I did here was multiply and divide by r. So I actually get that I have n over r here and n over r here. Now if you remember also, a to the b to the c power is equal to a to the b times c. Right now we have a multiplication in our power, in our exponent. So I'm going to rewrite this in this form instead, where I take this power to another power. What we're going to end up with is p 1 plus 1 over n divided by r, the n divided by r, the rt, like this. All right, now here's the tricky part. This might be a little bit tricky because it's probably new to you. If we're letting n go to infinity, all we're saying is that this exponent here and this denominator here are going to infinity at the same rate. So they're just increasing without bound. Now in our case, we have 1 plus 1 divided by n divided by r to the n divided by r, just looking at the interior term here. I need this n divided by r to be going towards infinity at the same rate that this n over r is going to infinity. And they will be because we have n divided by r and n divided by r. The same variables. R is fixed here. So as n goes to infinity, n over r is also going to infinity because r is fixed. Remember, it represents the annual interest rate. So it's fixed at some value. Now, as n goes to infinity, this term will be going to infinity slower, but because it's going to infinity, this term will eventually be approaching infinity as well. If we let n go to infinity, then n over r is also going to infinity. So we're getting that this and this are going to infinity at the same rate, which will mean that this entire term will be approaching e. This will be p times e to the rt, like this. And this will be our new formula for continuously compounded interest. Definition. Continuously compounded interest is calculated by the formula A of t is equal to e to the rt, where A of t is equal to the amount after t years, e is equal to principal, r is equal to the annual interest rate, and t is equal to the number of years. Now, we did problems like this in the last section, so I am going to count on you to be able to do this on your own without an example. Try one. If 2,000 credits is invested at an interest rate of 3.5% per year compounded continuously, find the value of the investment after 8 years. That's going to be it for today. I will see you all at the next lecture.